Hello everyone, welcome to Computer Science 227, lecture number 5. Today we're going to start a new topic, Introduction to Recursion. It's honestly one of my favorite topics in the whole computer science, I would say. So in the whole field of computer science, what I love the most is recursion, dynamic programming, and in Computer Science 350, there are a few topics that I really love. Okay, so but recursion I think is amazing. It might be challenging to understand at the beginning, but then once you get ahead of it, you're definitely going to enjoy that. Okay, so what is recursion? Recursion is very similar to, like in math and calculus, we have a term called recurrence. Okay, so if I say recurrence, okay, recurrence relations. Basically, it shows a function which is defined through itself on smaller arguments. Okay, for example, factorial, right? How do you define factorial? Okay, so it's n factorial is equal to n times n minus 1 factorial. Okay, and 0 factorial is equal to 1. So you see, kind of like, you're not saying that f of n is equal to, I don't know, 5 plus n, right? You're not saying that, I don't know, somewhere here, that f of x is equal to x plus 2. You're not saying that. So that's that is very simple to calculate, right? Because if I have f of 10, right, so 10, that would be 10 plus 2, that would be 12, okay? But, sorry. But here we have f of x, which is equal to f of x minus 1, for example, right, plus 2. And in this case, in order to calculate f of x, I need to calculate f of x minus 1, right, and then add 2. But how to calculate f of x minus 1, right? That would be, I need to kind of unwrap it again. So f of x minus 1 is going to be f of x minus 2 plus 2, okay, and then also plus 2, okay. But how do you calculate f of x minus 2? Okay, so that's going to be f of x minus 3, okay, plus 2, plus 2, plus 2, okay, and so on and so forth. Of course, like, that sounds like an infinite loop, right? So just f of x is defined through f of x minus 1, f of x minus 1 is defined through f of x minus 2, f of x minus 3 is defined through f of x minus 4, right? And then that loop has to end somewhere, right? So again, it just sounds like a loop. So, you know, like in any loop, you have a base condition, right? So the moment where you need to stop. Here in recursion also, there is something which is called a base case, okay? That is the moment when you also need to stop, okay? So for example, you would stop when x is equal to 0, okay? When x is equal to 0, okay? So in this case, if I'm trying to calculate f of 10, okay, then I'm going to unwrap it, okay, only 10 times. And at that moment, it's going to stop. And which basically is going to mean that is going to be, so if f of x is equal to 0, then it would be what? F of 1, right? No, sorry, let's do it. If f of 0 is equal to 0, then it's going to be, f of 10 is going to be 0 plus 2 times 10, right? So it's going to be 20. Okay. Yeah, so that's basically it. And what's interesting is that I think theoretically, okay, so in theory, well, like in this case, in theory and in practice, right? Anything, so any code written with loops can be rewritten using recursion and vice versa. Okay, so you can achieve exactly the same results with the loops and recursion. Okay, recursion is just a lot of times much more convenient, and it's like intellectually a bit more challenging to understand. Okay, There are some tasks though which are, I don't know, insanely difficult to write using loops, and it's super easy to write using recursion, and maybe even vice versa. I'm not sure though. I'm not sure. Maybe there are some situations where you can easily write it with loops, but you can't do it with recursion. But I don't think I've never seen them. But there are some cases where you can definitely write stuff using recursion, but it's very difficult to do the same thing using loops. Okay, so what is recursion? Okay, it's a programming technique where a function, well, I guess like in which, right, the function calls itself. Yeah, function, subroutine, method, okay, calls itself. Okay. Most importantly, what do you need to remember? There are three parts of recursion. Okay, like three vital parts. Okay, if you miss at least one of them, then nothing's going to work. If you miss at least one of them, so you need to keep track of all three. Okay, otherwise nothing's going to work. First part. Okay, so that base case. Let's call the base case. So in other words, basically you need to tell when recursion stops. Okay, when to stop recursion. You need to tell Java like, hey, unwrap that function. Okay, define the function through itself, but please stop at some point, otherwise it becomes an infinite loop. So that's the first condition. Second part, without which it's not going to work. That method or function needs to call itself. Okay, so again, the base case, the function needs to call itself, and the function needs to call itself on decreased parameters. Okay, so parameters needs to be changed. Parameters needs to change. Parameters needs to change. Parameters needs to change. Okay, so those three vital parts. Okay, without them, nothing's going to work. Okay, so let's give an example. So we're talking about factorial here, right? Okay, so let's try to see how to calculate a factorial. Okay, so what you do is take number n, right? For example, 10. You multiply that number 10, okay, by 10 minus 1 factorial, which is non-factorial. And then you do the same thing again, okay? So let's try to do that. Let's create a function. Public int factorial, okay, and we're going to take an integer n. Okay, so let's first off, let's do it with the loops. Okay, so iteratively. What do we need to do? For example, if we're calculating again 5 factorial, right? So let's say our n is equal to 5, right? And then what do? We multiply 5 by 4, by 3, by 2, by 1. Okay, so basically multiplying all the numbers between 5 and 1. Okay, so using loops, it's pretty easy to do, right? So we would say int product is equal to 1, right? Then we would say while, okay, then I'm going to do what? Product times equals n, okay, n minus minus, and I'm going to do while what? While n is greater than 0. Okay, so once n becomes 0, I don't want to multiply it by anything. Okay, and then I'm going to return what? Return product. Okay, so let's do that. Okay, factorial 5, and this one needs to be static. Okay, so let's see if it works. 120. Okay, so 5 by 420, that's 60. Okay, yeah, so that's 120. Okay, perfect. So that's how you do it iteratively, so using loops, right? Now let's do the same thing using recursion. Okay, here's how to do it using recursion. So again, iteratively, and then like the other approach would be recursively, which means we're going to do the same thing using recursion. Okay, so how to do that? Again, we need 3 parts. Okay, the very first thing that you need to write is the base case. The base case in 99% of the time consists of the if statement. If, okay, if something is true, then we need to stop. Okay, how do we stop? We return, make a return statement. So in this case, we're going to return n. Okay. Next, if we are not stopping, then we continue. We're going to continue execution. Okay, and then we need to come to the other two steps. So function needs to call itself. Okay, which means somewhere here. Okay, in our case, it's going to be pretty simple. It's going to be immediately. We need to call a function from that function, which means we need to call factorial inside of factorial. Okay. And how do we do that? Hold on. So if we do 5, okay, now we're going to do this. Return n times factorial of n minus 1. Okay. And if n is equal to, when do we stop? When n is equal to 1, right? So we'll go 5, 4, 3, 2, 1. Okay, so when n is equal to 1, we're going to return 1. Okay, so I think that should work. Let's see. Perfect. Okay, so now let's see how to. First off, let me show you again those 3 steps. Okay, the first one is the base case. Okay, so the base case is almost always is the if statement. Okay, which explains when to stop. Secondly, function calling itself is here, and thirdly, okay, parameters need to change, and that's here. So if factorial is coming for variable n, then the next time we're calling it, it has to be decreasing. It has to be getting closer to the base case when n is equal to 1. So the first, originally n is going to be equal to 5, then it's going to be equal to 4, right? And which is getting closer to our base case, which is 1. So now let's see what happens. Okay, so let's see what happens. Let me show you so-called stack trace. Okay, so that's going to be a stack which is created inside of Eclipse, okay, and which tracks what methods are being called. Of course, at the very beginning, the very bottom, we have the main method. Okay, this one is called first, main. Okay, and then main method is going to do what? It's going to call factorial on 5. Okay, so here we're going to have factorial on 5. Okay, hope it makes sense, right? So again, main method, we're coming over here, we're calling factorial on 5, right? So I'm getting over here, factorial n is equal to 5. Now let's see what's going to happen here. It's going to compare 5 to 1, it's not the same, okay, skipping this, and then multiplying, so then it's going to say return, right? If we just said return n, then it would just return 5, that's it, right? But we said that it return n times factorial, which means before returning, it needs to calculate factorial of n minus 1 first, right? So that's why what it has to do, it has to call the same function again, factorial, but now on 4. I'm just going to say f, okay, on 4. Now let's see what happens. Coming back over here, n is equal to 4, right? So keep in mind that this n, 4, has nothing to do with that n, which is equal to 5, okay? So you see they're located in different parts of the memory. So each one of those blocks is going to be a separate copy in the memory, okay? So again, that's stack, okay? That's located somewhere in the memory. It keeps all the values for all the variables Okay, for the main method, everything is located here. For factorial on 5, everything is located here, which means all the code that n is equal to 1, this one, everything is here. For f of 4, basically, there will be another copy. Okay, now, now let's see what's going to happen here. Sorry. We have f of 4. Okay, if n is equal to 1, 4 is equal to 1. That's not true, of course. Skipping this. And then we're going to return 4 times factorial of n minus 1, which is 3. Okay, which means we're going to call another function. Okay, f of 3. Now, coming back here again. Okay, so f of 3, what happens here? 3 is not equal to 1, right? So skipping this. So we're going to return 3 times factorial of 2, right? So again, we can't return yet because we do not know the value of factorial of 2. That's why we have to call this function again. We're going to do that. Just going to do f of 2. Okay, so when n is equal to 2, again, we come here, we're skipping this, and then we're going to return 2 times factorial of 2 minus 1, which is factorial of 1, right? So we're going to call ourselves again. I'm going to call here, and then here we're going to say f of 1, right? But now, when n is equal to 1, this becomes true, okay? So now we actually not get into this line. We finally got our base case, so we're not going to repeat this cycle anymore, and we're going to return 1, okay? So we return 1 where? We return 1. Okay, we're going to return 1 back over here. Okay, so here we're going to return 1. Now from here, where did we stop when we were in when we were in f of 2? Where did we stop? We said return 2 times factorial of n, which is 1, right? So factorial of 1 becomes 1. Now here we the whole statement becomes return 2 times 1. Okay, so we're going to do this. So here we're going to return 2 times 1. Okay. Now in f of 3, where did we stop, right? At which moment we went from f3 from f of 3 to f of 2? At which moment did we do that? At the moment when we said return 3 times factorial of 2. Okay, factorial of 2 is calculated, it's 2, okay? So now it's going to multiply 3 by 2 and return back to f of 4. Okay, which means it's 2 times 3 is going to be 6. Okay, now where did we stop in terms of f of 4? At which moment we went from f of 4 to f of 3? Here also, when we said return 4 times f of 3, which is 6, so it's going to be between here and here, it's going to return back 6 times 4, which is 24. Okay, and now at the very beginning, when main called factorial 5, where did we stop in terms of factorial 5? Here also, right? We always stopped here. When we said return 5 times factorial of 4, which is turned out to be 24. So now we return back what? 24 times 5, which is 120. Okay, and then the main method just prints out 120 and returns. Okay, so that's how it works. It's basically kind of like an onion. You have layers, you're just removing those layers, you're unwrapping this thing, okay, and then at the very end you are you're coming back to the same base of the letter. So you see, main calls factorial, factorial calls factorial, factorial calls factorial, factorial calls factorial, factorial calls factorial on different arguments, right? So you see how the arguments are changing, by the way. So first of n was 5, then became 4, then 3, then 2, then 1. Okay, and 1 becomes a base case, so it doesn't go any further. And that is the reason why it's so important to be slowly approaching your base case. If here I make a mistake in terms of the base case, then nothing's going to work. Imagine, for example, that here I said instead of 1, I said 6. Okay, so imagine I said if n is equal to 6, okay, and then I would call it on 5. So it will be decreasing the argument. It will be first 5, then 4, then 3, then 2, then 1, and then it wouldn't stop. It would go to 0, -1, -2, -3, and it would just never approach the base case, and just kind of like an infinite loop. It's never going to stop. Okay, there is no stopping condition. And in this case, what is going to happen is that it's going to be infinitely calling, a factorial will be infinitely calling itself. Of course, nothing is infinite. It will be just calling until, as long as computer has memory, computer has a finite amount of memory, and that will be called stack overflow. Okay, when it runs out of memory, it's going to stop. That's why, again, it's very important that you change the parameter, approaching your base case slowly. 5, 4, 3, 2, 1. Okay, and then you stop at 1. Cool. Hope it makes sense. Okay, so again, three parts: base case, okay, which is this. Otherwise, it's not going to work. Function needs to call itself, so which means somewhere here inside of factorial, you need to call the same function factorial, and you need to always change the parameter. Okay. Another mistake which I see a lot is this: what if I forget to change n-1 to what if I get to change n? What if I just keep calling on n? So imagine this: you have 5, right? Factorial 5. Then instead of calling factorial 4, it would also call factorial 5. Okay, so it would miss the base case, call factorial 5 again, missing the base case, call factorial 5 again, missing the base case. You see, it would not be approaching the base case, which means, again, it's not an infinite loop, but it's stack overflow. So that's something to keep in mind. Cool, okay. Yeah, so that's basically, again, yes, recursion is a technique that leads elegant solution to problems that are difficult for the program using, that are difficult to program using simple loops. Okay. Here's an example also. Factorial 4 calls return 4 times factorial of 3, which in case calls return 3 times factorial of 2, which in case does return 2 times factorial of 1, which in its turn does return 1 times factorial of 0. Factorial of 0 is the base case, return 1. Okay, so return 1 over here. 1 times 1, that is 1, returning 1 over here. 2 times 1, okay, returning 2 back here. 2 times 3, returning 6 over here. Return 6 times 4, returning 24 over here, and that's it. So factorial of 4 will be 24. Okay, so you see, you kind of have a ladder. Okay, so you kind of go down the ladder and then you go back up. Okay, that's how recursion works. Okay, same thing with Fibonacci. Okay, you're probably familiar with Fibonacci sequence, right? How the rabbits population is growing, right? So maybe let's do the same thing, Fibonacci. Okay, so Fib. Okay, Fibonacci. So if you try to call Fibonacci, okay, of 5, how do you define a Fibonacci? So first off, you need to take a look at how that function is defined in math. Okay, Fibonacci. Okay. Okay. Yeah. So here's how it's defined. F of n, or like x of n, is equal to x of n minus 1 plus x of n minus 2. So if we try to convert that to math, to more formal math, okay, or like then it's going to be so Fib of n is going to be equal to Fib of n minus 1 plus Fib of n minus 2. Okay. So here, instead of like just n times factorial, right? So in this case, so here, what did we have? We had factorial of n is equal to n times factorial of n minus 1. Okay, so here we're kind of defining a function through itself, and here we're doing it kind of twice. So here Fibonacci is equal to 2 Fibonacci's before. Okay, Fib1 minus 1 plus Fib1 minus 2. Okay, now how to translate this into English? Sorry, not English, but computer science. First off, we need to find the base case. Again, if n is equal to what, then we're going to return. So in this particular case, we're looking for the lowest. When do we stop? Okay, so obviously, if we're talking about Fibonacci of 10, it's going to be Fibonacci of 9 plus Fibonacci of 8. Then Fibonacci of 8 is going to be Fibonacci of 7 plus Fibonacci of 6, and so on and so forth. So again, we're going down the number line. But when do we stop? At which moment are we going to stop? I guess it's going to be 0, 1, right? Yeah. So Fibonacci of 0 is 0, Fibonacci of 1 is equal to 1. Perfect. So if n is equal to 1, then we're going to return 1. Else, if n is equal to 0, then we're going to return 0. Okay, and else, okay, like this, we're going to do this, okay, which means we're going to return Fibonacci of, again, decreasing the parameter n minus 1 plus Fibonacci of n minus 2, like that. Okay. Yeah, that's it. So now let's take any number, let's say 14. Okay, and let's see if it's going to adapt to 377. Okay, 14. 14. Okay, Fibonacci 14, and I really hope it's going to be 377. Yes, perfect. Okay, worked out well. Cool. Okay. Okay, so how to develop a recursive method. Okay, so the method is implemented using if-else statement or switch that lists different cases. Okay, so I would not recommend using switch, but that's what the book says. I'll recommend using if statement or if-else statement. Create one or more base cases. Okay, so here we had, like you see, kind of 2 base cases. Usually there is only one, usually. Every recursive call reduces the original problem. Okay, so problem may be confusing word here. Every recursive call is decreasing the argument, the parameter. Or to make it more specific, it's it makes the argument approach the base case. Because it's possible that you would, in some recursive calls, you would start from 0 and then you'd approach, let's say, 100. Most of the times, though, you start somewhere, let's say, I don't know, at 100, and then you approach in 1 or 0, usually. Okay, so you decrease the original problem, bringing it increasingly closer to the base case until that case comes true. Okay, in general, to solve a problem is recursion. You break it into subproblems. Each subproblem is the same as the original problem, but smaller size. You can apply the same approach to each subproblem to use it recursively. Cool. Hope it makes sense. Again, of course, it's. I understand that may be, I don't know, challenging at first. Okay, but it's just practice. You just practice. It's not rocket science. It's not that difficult. Okay, so just don't be afraid of it. We'll go ahead and start practicing. I prepared a couple of problems for you. Okay, how to do this. Let me know if you have any questions about that. Okay, so on Thursday we're going to have a quiz, and in the quiz I'm going to ask you some theoretical questions about recursion, and also I'll ask you to solve a few problems using recursion. Okay, in code. Hope it makes sense. I'll see you guys later. Bye bye.